Hi there. Thank you for coming to the first of the Science Squad's lecture series. I'm Arya Rao. I'm a director of the Science Squad, and today we're going to be hosting Dr. Anil Venkatesh, who currently works at Ferris State University, and he will be presenting on the physics of music theory. And without further ado, I'll just let him go ahead and start presenting.
Okay, thanks, Arya. So today I'm going to give a talk on some work that I've done in what I'd call mathematical music theory. This work has been ongoing for about 2 years, and we finally have some results that we're going to write up into a paper. So I'm going to mix in some demonstrations with my guitar, just so you have a sense of what the music sounds like. And otherwise, I'll show you some slides that go through the project. Anyhow, let me switch over to the slides. Okay, so this project has to do with tuning. And when I say tuning, I'm talking about what pitches you decide to use on an instrument. So the thing is, most pitches don't sound good together. If you just play two random pitches on an instrument, you're not guaranteed that it will sound like music. So why is that? Well, you have this jarring sound if you just play two random pitches, and that's a result from something called the Beats phenomenon. So I'll show you a picture of the Beats phenomenon, but I'll also play it on my guitar so you can hear it. So what you're looking at is, in blue, a sound wave. Now, waves in the air are created by a vibrating string or vibrating membrane, and that creates a variance of pressure in the air. Now, if you have multiple different waves and they overlay, it can sometimes create a wobbling effect that doesn't sound very pleasant to the human ear. So I'll switch over to my camera. And what's going on here? Yeah, okay. And I'll play a couple pitches so you can hear what's going on. So if I play two notes that are quite close together, you're not going to hear very much wobbling at all. It practically sounds like the same note twice. But if I change one of those notes a little bit, you're suddenly going to hear a wobbling sound. You hear that? Now, we can use trigonometry to prove that the closer those pitches are, the slower the wobbles happen, until they barely seem to happen at all. Ready? I'm going to bring the pitches together. No more wobbles. Okay, so getting back to the topic at hand, the issue that you get when you play two random notes is that they don't line up well, and they create a lot of beats that are perceived as dissonance. Okay, so now, of course, there are some pitches that sound really good together. And so here are some I put on the table. So starting with C, for anyone who's played piano or another similar instrument, you'll know that C and G go nicely together. And C and E go nicely together as well, but C and F sharp go very badly. Now, what I've got here is a list of overtones. When you play a pitch, you're actually hearing many different pitches at once. So for example, if I play this note, your ear hears that as a single pitch, but really it's a superposition of many different pitches, and here they come. And many more. So what I've got here in the columns are, for the fundamental note C, here are all the pitches that happen when you pluck that note. For the fundamental note G, here are the first couple, and so on. And you'll notice that if you go down a little bit in the C column, you get to 784.8. That's beats per second. And that matches up quite nicely with 783.9 in the G column. That means if you play C and G at the same time, those notes match well, and you don't hear very many beats. And again, with E, going all the way down to 1308, that's, once again, beats per second. That matches quite nicely with 1318 in the E column. That means playing C and E together will also sound relatively harmonious. But when you play C and F sharp together, there's no number that matches very well from the C column and the F sharp column, so you receive dissonance. That's why C and F sharp don't sound very good together. So how can we avoid dissonance, tune an instrument such that when you play multiple notes together, it sounds good? Well, those columns that I just showed you are the so-called overtone sequences. Those are all the different pitches that happen when you play a single note. We would want those overtone sequences to be closely approximated by the tuning. That means when you play a note, it should match another note's overtone sequence pretty well. But it's important that this holds for every note. It's not just the case that one special note and its overtones are well approximated. If you have that, what you've got is a bugle. So I'll switch over to the camera again to show you what I'm talking about here. Let's get this going. So on a bugle, you can't really vary the pitches, the fundamental pitches. You only have the one pitch that the instrument determines, which is like playing one string and all the overtones on it. So perhaps you'll notice this song. That's the song called Taps. It's a military song played on the bugle. Now, it's not a very it's not a song that uses a bunch of different notes because there's only a few that are available on the bugle. You don't have any valves to vary that up. Now, we want to tune an instrument that can be played in any key, not just whatever the fundamental key is of the bugle. So that's why it's important. That's why it's important for our tuning to work for every kind of overtone, not just the overtones of a single string. Okay, now a pretty good try at this is what's called 12-tone equal temperament, or the piano tuning. Now, how do you do that? Well, you just start at some pitch and go up a 12th of the octave, and that's your next note. And just keep doing that. You'll have subdivided every octave into 12 little steps. And it turns out that that does a pretty good job of approximating some of the overtones. Here's an example. Now, the overtone number 3, that's like going from C to G. It does a good job of approximating that. When I say minus 1.96%, that means only about 2% of the way from one key to the next on the piano. That's not something that most people can hear. The next overtone, however, is not approximated very well, and a trained musician can hear the difference. So what I'm saying is, even though you might grow up with a piano tuning, that tuning is kind of at odds with your own idea, your own ear's idea of what sounds good. So some keys played together on the piano will sound a little bit off, and some are even worse than others. So overtone number 7, you're off almost a third of the way to the next key. And overtone number 11, that's F sharp with respect to C, that's almost half of the way to the next key on the piano. So the upshot is that although piano tuning is a nice approximation, it's something that children can easily learn, it doesn't do a great job of creating nice harmonics. So what can we do? We could, of course, introduce more keys, make it so it takes 19 steps through the octave, or even 72 steps. And those approaches have been examined by composers. But there's another idea. And now this is a picture of a composer named George Sakura, and he pioneered the idea of the two-dimensional tuning. So if you see by his left hand, he's got his fingers on this two-dimensional grid of buttons. Now, it turns out if you have two different directions you can go in with the keys, you can create really tunings that really closely approximate the overtones. Therefore, they sound really good when you play multiple notes together. So here's George Sakura's idea. Now, if you arrange so that when you go up a row of keys, you go up by one octave, then all you need to decide is let me get the screen share off again. Right, so imagine this way. You've got a row of keys, and they're going up like you would on a piano. Now, if you raise your hands up, there's a whole new row of keys. And suppose whenever you do that, it goes up by one octave. Or if you go down a row, it goes down by one octave. All Sakura needed to figure out was, how big should that little step be from key to key, going horizontally, in order for that whole bunch of keys to match the overtones really well. So that's the problem he set out to solve. And he did a really good job of it. This was back in 1974. He came up with this special interval. It's a little bit more than a step on a piano. And when you tune an accordion that way, look at this improvement. Instead of being off overtone number 5 by 13%, 7 by 31%, the worst deviation was, in any case, was only 3%. So that means that if you tune a keyboard like that, you'll get much closer to the overtone sequences. You'll reduce those beats phenomenon, And in general, there will be a lot less dissonance when you create that music. So I heard about this, and I got to thinking, is it possible that there's an even better way to do it? George Sakura was doing this work back before computers, so he had to do it all by hand. Now we have computers. I wondered whether we could maybe find an even better way. So here was his approach. He was trying to figure out what that other interval should be, that little half step, and he called it x. And every overtone you're trying to approximate imposes a constraint on x. You can't just pick any number you want for x, or it might mess up one of the overtones. So the best choice will be the number for x that minimizes the worst error. What does that mean? It means if you're trying to approximate 5 different overtones, you want to figure out what's the step size so that none of those overtones sounds really bad in this tuning. We want to minimize the worst error. Okay, so my understanding is the audience has done a little bit of graphing of linear functions. Here's some applied graphing of linear functions for you. Each of these lines represents one of the overtones. Let's see how many there are. 1, 2, 3, 4, and 5. Okay, so there's 5 main overtones we're trying to approximate really well. The x-axis represents our choice of step size. That's the distance from one key to the next, musically speaking. And the y-axis represents how far away we are from being perfectly on that overtone. So let's consider this line right here. If we were to choose a step size of 117 cents, then the height of that line there is about 3.5. That means that we're 3.5 cents away from being perfectly on that overtone. Whereas if we were to choose a smaller step size, we'd get a better and better approximation of that overtone. But notice, choosing a smaller step size makes these other overtones have a worse approximation. We're trying to figure out what x value makes all the lines as close to the 0 height as possible. And you can probably tell it's right here. That's the x value that brings all the lines as close to 0 as possible. So George Sakura found that out by hand. This is called a mini-max problem. Well, unfortunately for Sakura, it turns out that the problem's not quite so simple. Here's why. Well, I told you that each overtone imposes a linear constraint. Think of it as a linear function that we're trying to solve with. Actually, there's more than one choice for each overtone. That means that we can swap out some of those lines with other lines. And maybe if you swap out one line with another one, you get an even better solution. So I'll illustrate that here. So check this out. Instead of that bottom line, we can derive mathematically that there's another constraint we could use instead. And if we put that one in instead, there's a slightly better solution. Okay, here's another picture you can see. The really slanted line is the new one, and it makes everything brings everything a little closer to the x-axis, so it would be a better solution. Okay, so this problem gets a lot harder because you don't just have 5 lines, you have infinitely many lines, and you've got to make a smart choice of which lines to use. So as you can see, this is a small improvement from George Sakura to that new line I introduced. All right, so the kicker though is that you can't just throw in whatever line you want. Sometimes that line you're putting in would mean that it's being played on a very large instrument, maybe an instrument that's too large to be realistic. So we have to answer the question, what kind of instrument dimensions should we be working with anyway? How big of an instrument could there realistically be? Well, when I thought about how big instruments could be, I thought of organs. They're pretty large, right? So here's an example. It turns out that these are about, at largest, maybe 4 rows of about 60 keys. Okay, so when I set out to solve this problem with my undergraduates, I decided let's consider all instruments up to that size and figure out the best way to tune them. Maybe there'd be a better way than the 1974 result. Okay, so here are the constraints that we put to ourselves. Obviously, we want minimum deviation from the overtones, also known as harmonics. That's as to say, we want the tuning to sound as good as possible. We'd like to have the minimum number of octaves and steps per octave. That's just saying we'd like the instrument to not be as huge as you can imagine. We'd like for it to be as few rows and as narrow as possible. So for a fixed number of harmonics, let's say 5, the research question is to figure out the best possible tuning or temperament for each dimension of instrument. So here's a quick example. Across the top, those are three different choices of lines given by the x-intercept and the slope. So we can choose one of these lines for the first overtone. We choose one of these second row for the second overtone, and so on. And we can pick anything from the first row, match it with anything from the second row, and so on. That's a whole bunch of different ways to match these lines. So one way to figure out the best choice of lines would be to kind of imagine starting at the top and percolating down. So that the diagram I'm just showing you is picking the first line from the first row, the first line from the second row, and from the third row, but then trying out this second line in row number 4 and this final line in row number 5. So we could go through all that and do the same kind of computation Sakura did to figure out the maximum deviation. But then we go back to the beginning and try a different path, a different kind of percolation through this matrix. Sorry, we're getting a little bit, little email notification there. Okay, so the job is to percolate through this matrix. Every different path you pick is a different way of choosing the lines that you're going to solve for. Well, the thing is, you end up with a lot of lines, a lot of paths, and a lot of different ways to percolate through. So if each computation takes just 0.05 seconds in a kind of in the size of problem we're trying to solve, that's 12 and a half years of runtime. And if you make that problem just a little bit bigger, it's 21.4 million years. So as soon as we set up this problem, we realized we need a smarter way to percolate, a smarter way to avoid trying every single possibility. Okay, that's where the backtracking algorithm comes in. Now here's the idea. Let me go back up to the diagram. So suppose you start at the top and you try percolating down, you've picked a couple lines, and you realize, you know, this is not promising. We're already so far away from the x-axis, throwing a couple more lines on is never going to make the problem better. At that point, the algorithm says, forget it, backtrack and try a different path. It's not going to, going to the end of this path is not going to tell us anything we don't already know. So yeah, to sum up, the algorithm says, start from the top, and if at any point it seems like you've already got a bad choice of lines, abandon it and try a different path. All right, so here's our main results. Our backtracking algorithm cut that 12.7 year runtime down to only 6.25 seconds. That means that in this whole big mess of lines that we're trying out, most arrangements of them are very bad. And so our algorithm quickly avoids them. And there's only a couple that are good, which our algorithm eventually finds. Now, how about for that million-year problem? We actually solve it in just 49 seconds. That goes to show that, for a number of reasons, this problem is very well suited for backtracking. Got to be careful, right? Because with backtracking, if you are unlucky, you might end up trying the choices in such an order that every choice is slightly better than the last one, and you'll never save any time at all. It turns out in this particular problem, most choices are so bad that the algorithm avoids them and gets really great savings in runtime. So what kind of tuning results did we get? Okay, so what I've got here is down this column is the number of rows the instrument needs to have, the number of octaves. And across is the number of keys it's going to need to have. Purple right here is Sakura's solution. 3 rows or 3 strings and 22 frets. Well, I have to say Sakura did a great job by hand, because the first tuning we found that was better than his needs 2 rows and 36 frets. So it's quite a bit longer. And that improved his tuning by 11%. The next one needs 4 rows, 43 frets. And that also was an 11% improvement, 11 and a little bit. The next one, as you can see, it's getting quite long now. It's about as long as one of those. It's getting to be about as long as one of those pipe organ keyboards. Well, 32% improvement was possible. And going through, we actually found up to a 70% improvement to Sakura's tuning, as long as we introduced a pipe organ-sized instrument. So that was the result of our research. we started with this problem from 1974 that was crafted before computers were invented, and we tackled it using a couple techniques. One, we used linear algebra. That would be the mathematics that arises from studying linear functions. Specifically, we graphed a bunch of functions and found that there's this idea of a minimax, this concept of taking several different linear constraints that aren't compatible and figuring out how to make them all as good as possible jointly. That's a very popular technique, and there's many applications of it beyond music theory, to be sure. Beyond linear algebra, what did we do? We also used this computer science technique of backtracking. We took a problem that, if you try to solve it in a sort of off the top of your head kind of way, would be impossible. It would take millions of years. But we applied some logic based on the structure of that problem to avoid wasting our time with possibilities that we knew weren't going to be promising. And we cut that runtime down to under a minute. Altogether, we got this really neat result that if you want to tune a pipe organ in the best possible way, well, you can beat that 1974 result by 70%, and beat, by the way, the 12-tone equal temperament by a lot more than that. So we're really happy with the result, and the undergrads who worked on it will be publishing a paper with me in the coming year. That's it for now. Thank you.
All right, everybody. Thank you so much for coming out, and we hope that you come to our future lectures. We have a lecture next week, Monday, featuring Mr. Paul Filio from Northwestern University. He's going to be talking about political science. But for now, I'd just like to say thank you for Dr. Anil Venkatesh for coming out and lecturing for you guys. And until next week, have some more fun with some science. See ya.